Usually, when we look at complex software, there's this expectation of magic,
Oh, definitely. We want it to be seamless.
right? It operates like this impenetrable black box of algorithms and data. You tap a glossy icon on your phone, a car arrives at your exact location 3 minutes later, and the software engineer just points at it and says, "There it is. It works."
Yeah, we really prefer our technology to feel like effortless wizardry because honestly, the alternative, acknowledging how fragile it all actually is, can be a little unnerving.
But then you step into the world of actually building that software. You peek behind the curtain, and suddenly that illusion of magic just completely evaporates.
Completely, it's just gone.
We're left looking at this landscape of brutal logic, complex design, and inevitable cascading failure that is uh, remarkably human.
It's very human.
So today, we're tearing apart that magic. We've got a fascinating set of lecture notes from an MIT Introduction to Programming in Java course.
And this dates back to what, January 2010?
Exactly, January 2010. And, on the surface, that might sound like we're about to read a really dense technical manual.
Right. I mean, if you aren't a software engineer, just hearing the word Java might make you want to tune out entirely.
Which is exactly why the mission of this deep dive is so important. Even if you have never written a single line of code in your life,
Never even opened a command prompt.
yeah, even if that thought makes you break out in a cold sweat, stick with us. Because these MIT notes aren't just about syntax.
No, they're really a masterclass in organizing complex information.
Right. Problem solving under pressure, building foolproof systems in literally any area of your life.
We are really looking at foundational mental models here. When problems get too massive to hold in our brains all at once, we need architectures to manage that complexity.
Setting the stage here. The source notes point out early on that every single Java program starts at what's called a main method.
Yeah,
The notes use this example called a simple draw class, which kicks off a whole graphics program. And even though you might have like hundreds of different files and classes, there's always this one single point of entry.
this is the front door.
Exactly, the front door. But simply getting a program to walk through that front door and run doesn't mean it's actually a good program.
Not at all.
Okay, let's unpack this. What actually makes code good?
Well, the MIT notes establish that just making a program run is really the bare minimum. They outline 4 core pillars of good program design.
Okay, 4 pillars.
And what's interesting is the natural tension between them. So the first pillar is correctness. I mean, obviously, it has to have no errors and actually do what it's supposed to do.
Right, the non-negotiable baseline.
Exactly. But then we introduce the second pillar, which is that it needs to be easy to understand.
Okay.
The third pillar demands it must be easy to modify and extend. And the fourth pillar is good performance, meaning it needs to be fast and efficient.
And those pillars often fight each other, right?
Oh, constantly.
Sometimes writing the absolute fastest, highly optimized code results in something that looks like complete gibberish.
Which totally violates the rule that it needs to be easy to understand. It's a classic engineering trade-off.
Yeah.
You can build a Formula One car for pure speed, but it's not going to be easy for the average mechanic to just open up and modify.
I want to zoom in on that second pillar, actually.
Yeah.
The idea that code must be easy to understand, because the source material spends a surprising amount of time on the grammar and styling of coding.
It really does. It lays out very rigid naming conventions.
Yeah, so variables, which hold your data, have to be nouns starting with a lowercase letter.
Right.
And if it's multiple words, you capitalize the next word, like typing hi,
Yeah.
and then score with a capital S.
Camel case, yeah.
Then methods, which are the actions the program takes, have to be verbs, like get and then size with a capital S.
Uh-huh.
And classes, the overarching blueprints, are nouns that start with an uppercase letter, like shape.
It closely resembles the strict grammatical rules you learn in, like, an elementary school language class.
So what does this all mean? Because I really have to push back on this level of pedantry.
Okay, let's hear it.
The computer ultimately compiles all of this down into microscopic electrical switches,
Yeah.
just ones and zeroths.
True.
The processor doesn't care if I called my variable high score or banana73 or just the letter X. If the machine doesn't care, aren't these naming rules just programmers being obsessive control freaks?
If we were only writing for the machine, you would be absolutely right. But the core insight here is that we aren't writing code for the machine.
We're not.
No, code is written for humans.
We're writing for the human reader.
Exactly. Software is read infinitely more times than it is ever written. You might write that variable once, but over the next 5 years, your teammates have to read it.
Or entirely new employees who inherit your project.
Right. They have to read it, understand its intent, and modify it without breaking everything else. Establishing this strict visual grammar reduces the cognitive load on the human brain.
That makes sense.
If I see a word starting with a capital letter, I instantly know it's a class. I don't have to pause, break my focus, and go look it up.
It's the exact same logic behind road signs, isn't it?
Oh, that's a great comparison.
The physical car driving down the street doesn't care what color the stop sign is. But the human driver needs it to be read every single time in a standardized octagonal shape.
So their brain processes stop instantly, without conscious thought.
Right. Predictability is safety.
And this philosophy of predictability drives what the notes call good class design. A well-designed blueprint makes your fields, your internal data and your methods private by default.
Meaning other parts of the program are completely blocked from seeing or touching that data.
You lock it in a vault. You only make things public if you absolutely must.
Like if some outside piece of code legitimately needs access.
Yeah, but you don't just leave the vault door open. You create a highly specific public method, say, public in getBar, whose only job is to retrieve that data and hand it over.
You force everyone to go through the proper channels.
I have to.
It's like submitting a request form to a bank teller instead of just walking into the vault and grabbing the cash yourself.
Exactly. It stops other parts of your massive program from accidentally overwriting or wrecking your crucial data.
But, creating private vaults and naming your variables perfectly doesn't stop human beings from writing flawed logic.
Unfortunately, no. The system will still inevitably break.
And when that predictable human error occurs, the MIT notes don't just say fix it. They offer this really rigorous scientific method for tracking down the ghost in the machine.
Yes, the 6-step debugging process. It's an incredibly robust framework.
Not just for software either.
No, for performing root cause analysis in almost any crisis scenario.
Step 1 of this process is hilarious to me, though.
Oh, I know what you're going to say.
The notes literally state, Step 1, don't make mistakes.
Yeah.
When I read that, I laughed out loud. That is exactly like telling someone who is learning to juggle, Step 1, don't drop the balls.
It really does sound like that.
It's utterly unhelpful on its face. How is not making a mistake a debugging step?
It sounds incredibly facetious, I admit. But looking at the broader context of the lecture, they are talking about preventative design.
Okay, preventative design.
They mean designing your workflow so that you systematically avoid introducing chaotic variables. And they highlight 3 concrete ways to do this.
What's the first one?
First is reuse. If there is existing battle-tested code that already does what you need, use it. Don't write it from scratch and inject new unknown flaws.
That's smart.
Second is design on scrap paper. Map out the visual logic of your objects before you ever even touch a keyboard.
And the third strategy they emphasize is writing what they call pseudocode.
Right.
This is taking a plain piece of paper and writing down a high-level description of what the program is supposed to do using plain English.
You entirely ignore the semicolons and the specific formatting.
Because if your logic contains a fatal flaw when explained in plain English, translating it into perfect Java syntax won't save you.
Exactly. The logic is fundamentally broken.
Which brings us to step 2. Find mistakes early. The notes stress that the longer a bug lives in your system, the harder it is to extract.
So you have to test your design aggressively.
Specifically focusing on important intents.
Yeah, you have to map out all the possible paths a user could force your program to take and test at least one scenario for every single path.
The source gives a brilliant example of testing boundaries, which is notoriously difficult for programmers.
It really is.
Imagine you are writing a program to see if a number falls within a specific mathematical interval. Let's say from a lower bound x up to but not including an upper bound y.
Okay, the XY interval.
Right. You can't just throw one random number in the middle of that interval and say, yep, the program works.
No, because bugs love to hide on the edges where the logical rules shift.
So the notes outline a gauntlet of tests for that interval. You must test a number below the lower bound.
Right.
You must test a number exactly equal to the lower bound, then a number safely inside, then a number exactly equal to the upper bound, and finally, a number above the upper bound.
You have to poke every single edge of the logic.
Every single one.
And the notes push this even further by asking the programmer to consider the impossible.
Like what?
Like, what if the user inputs a lower bound that is actually greater than the upper bound? What if the 2 bounds are exactly equal?
Oh, wow.
If your software assumes X will always be smaller than Y and the user flips them, your program will likely shatter.
You just have to anticipate utter chaos from the user.
Always. To help with this, the source lists automated tools. They specifically point out the warning messages generated by Eclipse, the software environment they use.
And the rule is absolute, right? Always fix all warnings.
Always. Even if it seems minor, a warning is the system telling you something is unstable. They also recommend testing tools like FindBugs and Junit.
But the most conceptually fascinating tool they introduced for finding mistakes early is the assertion.
Yes, the assertion.
The name makes it sound like you're just confidently declaring something to the computer, but it functions much more dramatically than that.
It really does. It acts as an intentional tripwire. An assertion allows you to verify that your code's reality matches your expectations at a highly specific millisecond in time.
So how does that work in practice?
Well, the source uses the example of calculating marathon times. You have a program that subtracts the fastest runner's time from another competitor's time to find the difference.
Okay.
Logically, physics dictates that this difference must always be 0 or a positive number.
Right, a runner cannot be faster than the absolute fastest time.
No.
It's a physical and mathematical impossibility.
Precisely. So you write an assertion statement directly into the code, declaring assert difference is 0, 0. Assume the difference is greater than or equal to 0.
Got it.
When the program runs, it checks that statement. If the difference is indeed positive, the tripwire is untouched and the program just keeps running normally.
But if that difference somehow comes back as a negative number,
The tripwire snaps. The program intentionally and violently crashes, throwing an error right at that exact line of code.
it just pulls the emergency brake on the whole operation.
Exactly. Now, the notes do specify that you have to actively enable these tripwires.
How do you do that?
You run the program with a specific flag, a dash followed by E and A, standing for enable assertions. They are turned off by default.
I see.
But the underlying philosophy is profound. It is vastly safer for a system to crash immediately and loudly the second a logical impossibility occurs, rather than quietly letting that corrupted data ripple through the rest of the application.
Because that would ultimately cause a baffling failure 10 minutes later in a completely unrelated area.
Exactly.
I love that concept. Intentionally crashing to prevent a worse disaster. Okay, so we've practiced preventative design, we've set our tripwires, and yet a bug still slips through.
It always happens.
This is where we enter the heavy lifting of the scientific method, starting with step 3. Reproduce the error.
This is often the most frustrating phase. A bug that only happens randomly is nearly impossible to fix.
Right, you have to find a way to make the error happen consistently on command.
The notes advise creating what they call a minimal test case.
Which basically means isolating the infection.
Yeah, you strip away all the noise, you go back to a version of your project that worked, and you introduce your new changes one tiny piece at a time until the software breaks again.
So you eliminate any extra code that isn't actively being used.
Right, so you are staring at the smallest possible environment where the bug exists.
It's like trying to find a rattling sound in your car. You don't take apart the engine first.
No, you take all the loose junk out of the trunk and the glove box to make sure that isn't the noise.
Exactly. Then we hit step 4. Generate a hypothesis. What is actually causing the failure? The MIT notes emphasize a critical psychological hurdle here.
You have to question your own assumptions.
Right. Human ego gets in the way of debugging.
It really does. We stare at a block of code and think, well, I know that part is perfect, so the impossible variable must be coming from somewhere else.
But step 4 demands that you assume the impossible is happening. You have to suspect your own flawless logic.
Which is hard to do.
Very hard. Once you swallow your pride, though, and hypothesize that your perfect variable might be broken, you move to step 5. Collect information.
You need a way to peer inside the black box while it's running to see if your hypothesis is true.
So what's the tool for that?
The lecture highlights a very foundational Java command here, printing to the standard output, system.out.println.
It's a way to force the program to spit out text to your monitor.
Yeah, you sprinkle these print statements throughout your code like breadcrumbs.
Shining a flashlight into the dark room. You just ask the program, hey, what number are you holding right now?
Or, you can use the built-in Eclipse debugger to freeze the program in time and inspect every single piece of data.
Which culminates in step 6. Examine data. You look at the information you just extracted.
Does it prove your hypothesis?
If it does, you found the bug, so fix it. If the data proves your hypothesis wrong, you generate a new hypothesis and start the loop over.
It is the scientific method, purely applied to digital architecture. Observe, hypothesize, experiment, analyze.
If the best way to make debugging easier is simply having less code to dig through when things go wrong, That perfectly sets up the next major architectural shift in the MIT notes.
Encapsulation.
Encapsulation, or as I like to think of it, hiding the mess.
That's a great way to phrase it. As programs scale up, they quickly become too massive for any human brain to comprehend every single moving part.
So you have to start chunking behaviors together.
Right. And the foundational level of this is using methods.
The notes explain that methods allow you to write and test a block of code once, and then reuse it endlessly to avoid duplication.
It's a massive time saver.
Like, if you are building software for a public library, you don't write the 20 lines of code required to add a book to the database 50 separate times throughout your program.
No, you bundle those 20 lines into a single method called library.addBook. And whenever you need it, you just call the method name.
But the real power of methods goes far beyond just saving keystrokes.
Absolutely. Methods allow you to utilize a complex piece of logic without ever needing to understand its internal mechanisms.
The source explicitly refers to this as encapsulation or information hiding.
Yes.
The best analogy for encapsulation is ordering food at a restaurant. You walk in, you sit down, and you interface with the menu.
Okay, I like where this is going.
You tell the waiter, I want the burger. To get that burger, you do not need to know the exact temperature of the grill.
Right.
You don't need to know the chef's specific seasoning ratio. You don't even need to know the supply chain logistics that delivered the tomatoes.
That would be exhausting.
Exactly. You just pass in your request, and the kitchen, which is the method, handles all of that messy internal complexity and simply hands you back the finished burger.
The restaurant kitchen shields you from cognitive overload.
It does.
And the notes provide a perfect coding equivalent for this. That command we mentioned earlier, system.out.println, long less.
Oh, right. To print text to the screen.
We use it constantly. But do either of us actually know the underlying operating system calls, the hardware interrupts, and the memory management required to make individual pixels light up on a physical monitor?
I couldn't even begin to guess.
And the beauty is, we don't need to. That overwhelming complexity is completely hidden from us behind a simple method name.
It's brilliance.
Taking this philosophy a step further, the notes introduce objects.
Ah, objects. The absolute bread and butter of Java.
They take encapsulation to the next level. They bundle a related set of variables, which is the state or data, and methods, which are the actions, together into one unified package.
So instead of just a method that cooks a burger, an object represents the entire restaurant.
Exactly. Giving you a simple interface to interact with its highly complex internal behaviors.
Okay, so objects are great at hiding the inner workings of our code. But how do we handle a massive system that relies on dozens of different objects?
That is the big question.
Here's where it gets really interesting. This leads us to the final and arguably most powerful concept in the lecture notes, interfaces.
This is the moment we transition from merely organizing code to truly architecting a system.
Let me lay out the problem exactly as the source presents it to the MIT class. Imagine you are building a visual program called DrawGraphics.
Okay.
You want to draw a bunch of different shapes on a digital canvas. You have an array list of bouncing box objects, you have another list for some flower objects, and you have a third list for some car objects.
3 entirely different blueprints with entirely different internal data.
So how do you manage them? Without interfaces, you have to create a separate list just for the bouncing boxes. Then a second, completely separate list to hold the flowers, and a third for the cars.
Right.
When it's time to update the screen, you have to write a loop to go through every box and draw it, then a second loop to go through every flower, then a third loop to go through every car.
It creates a tremendous amount of structural friction.
And imagine expanding that. If you add 20 new types of shapes to your program, are you going to maintain 23 different lists and write 23 different loops every time the screen updates?
It's completely unmanageable. It directly violates that third pillar of good design we discussed, making the code easy to modify and extend.
So what's the solution?
The solution the notes introduce is the Java interface.
Okay, an interface. What is it?
An interface is a way to group different classes together based on shared behaviors. But here is the critical distinction. The interface does not contain any actual code.
Wait, no code at all?
None. It only provides a definition, which is called a signature.
Oh, so it functions as a legally binding contract.
Yes, exactly. You create an interface and name it something generic, like drawable.
Okay, drawable.
Inside that interface, you define a single method signature that says void draw graphic surface, meaning draw yourself on the screen.
But there's no instruction on how to draw.
Right, it's just an empty demand. Then you tell your completely different classes, the flower the car, and the bouncing box to all implement that drawable interface.
By implementing it, they are signing the contract. They
Exactly.
are promising the overarching program. I guarantee that regardless of how my internal kitchen works, I have my own specific way to draw myself when asked.
The resulting transformation of your main program is profound because all those diverse objects sign the same contract. Java allows you to throw them all into the exact same list.
Just one list.
You no longer need 3 lists, you just create one master array list designed to hold drawable objects.
That is so incredibly elegant. Instead of writing 23 different loops, you just write one single loop that marches down your master list, looks at every item and says, hey, I don't know or care if you are a flower or a car, but I know you signed the contract, so draw yourself.
And they all execute their own unique code. What's fascinating here is that you are interacting with complex objects without knowing their specific identity.
I can see how that's game-changing when you integrating code written by other teams.
Absolutely. You don't need to understand the physics of their bouncing box. You just agree on the shared interface.
But this incredible organization does come with a major catch, right?
It does.
If I take my complex bouncing box and drop it into a generic master list categorized only as drawable, I essentially put a disguise on it.
The interface acts like a pair of blinders on the program.
The source shows that if you try to command that box to change its movement speed while it's sitting in the generic list, say, using set movement vector 11, the program will throw a massive error
Yeah, it will tell you that movement commands are undefined.
because the generic drawable contract knows absolutely nothing about movement physics. It only knows about drawing.
Right.
Okay, doesn't that defeat the entire purpose? I group everything together to make my system architecturally clean, but the cost is losing access to the specific, unique abilities of my objects. Why make that trade?
It is the eternal tug of war in software design, standardization versus specialized functionality. But the MIT notes provide an escape hatch,
An escape hatch.
a technique known as casting.
How does a cast resolve that?
If you, the architect, possess the external knowledge that a specific item sitting in that generic list is, in fact, a bouncing box underneath its drawable disguise, you can force the program to take the blinders off.
Really? How?
You explicitly declare to Java, I know this generic item is actually a bouncing box, so treat it like one. The code looks like bouncing box pause, bouncing box
It's like checking a corporate ID badge.
Oh, how so?
You have a massive building full of people wearing the exact same generic employee badge, but you stop one of them and say, let me check your specific credentials. Ah, you're the server technician. Take off the generic badge, go into the server room, and fix the router.
A perfect analogy. Casting gives you the best of both worlds. You get the overarching, streamlined organization of interfaces for the bulk of your program.
But you retain the ability to drill down into highly specialized functionality when the situation demands it.
Exactly.
Incredible. So just to recap the sweeping journey we've taken through these lecture notes today,
We've covered a lot of ground.
we started at the grammatical foundation, learning that the style of code is designed to lower the cognitive load for human readers, not machines.
Right.
We explored the rigorous preventative design and the intentional tripwires of the debugging process.
The scientific method in action.
And finally, we climbed the ladder of abstraction, seeing how encapsulation hides the messy kitchen and how interfaces allow entirely different systems to collaborate seamlessly.
And the overarching takeaway here is that these are profound mental models for navigating complexity.
Not just in Java.
No, in life. Encapsulation is the ultimate framework for delegating tasks and trusting outputs. The debugging process is a masterclass in isolating variables during a crisis, whether that crisis is failing software or a failing supply chain.
And interfaces teach us how to find shared behaviors to unify disorganized systems.
It is an absolute masterclass in structured thinking.
Which leaves me with a final thought I want you, the listener, to ponder today. We talked about assertions, those intentional tripwires that violently crash a system the moment a logical expectation is violated, doing it early to save the program from silent, catastrophic failure down the road.
The intentional crash.
Yeah. What would happen if we built those assertions into our own lives? Think about your daily workflows, your long-term projects, or even your habits.
That's a fascinating question.
What are the boundaries where you should intentionally throw a red flag and halt all progress the moment an expectation isn't met? Sometimes letting a process quietly fail in the background is the most dangerous thing you can do.
Very true.
Where you need to install a tripwire. Thank you so much for joining us on this deep dive. Keep questioning your assumptions, and we will see you next time.